powerful. Okay, this is so simple yet so powerful. This variation principle. Okay. So first application that we'll discuss is in the case of simple harmonic oscillator. So we'll try to evaluate the ground state energy of simple harmonic oscillator using the variation principle. You might say that okay, that is not required because we already know we have solved the energy eigenvalues of a simple harmonic oscillator exactly. Okay, so why we do it? The whole idea is that this will give us an estimate how good is variation principle. Since we know the exact value, we'll see that what is the prediction of the variation principle. Okay, so using variation principle, we will estimate the simple harmonic oscillator. So we can write it, say, ground state energy. Let's see how to do that. So first we need two things for the variation. First thing is Hamiltonian. Hamiltonian we know square by 2m plus half m omega square x. Second is we require a what is called an trial wave function. Okay. We can since we live in the position space or in the position representation, so it will be variation principle mostly it works in the position representation. In position representation, this Hamiltonian, as we have already discussed at a length, it will be. Remember, we are considering only a one-dimensional problem. Okay, now next thing that we require, so first we require the Hamiltonian. Second thing we require the trial wave function. So we will introduce a trial wave function. We don't know. I mean, of course, we can find out the wave function. Actually, we have done it by solving the time-independent Schrodinger equations. But for the time being, we will not do anything. We'll just write down a trial wave function which has some nice properties. So here is our trial wave. Psi x equal to a e to the power minus bx. So b is a constant and a is determined by normalization. And then what we'll do is that we'll try to vary this b so as to minimize the expectation value of Hamiltonian. Okay. Before getting into that, let us see. Let us use this normalization condition to determine A. Okay. So minus infinity plus infinity mod psi square dx equal to what? Right? That is the normalization condition. So this implies mod a square integration e to the power minus 2bx square dx minus infinity plus. Right? This is equal to 1. So this integral we have to do to determine the value of A. Okay, it's not so difficult to do this integral. The first thing that we can observe about this integral is this e to the power minus 2bx square. Is it an even function or odd function?
Even function, sir.
It's because if x changes sign, this remains the same. If that is so, then instead of integrating it from minus infinity to plus infinity, we can simply integrate it from 0 to infinity and multiply it by 2. Because the value of this integral from minus infinity to 0 will be same as the value of this integral from 0 to infinity. Second point is that do you know how to do this integral? Anybody knows? Okay, in order to do this integral, let's substitute y equal to x square. And then dy will be 2x dx. So in other words, we can write dx to be equal to half y to the power minus of dy. Right? Is it clear? We substitute it over there. 2 mod a square equal into 0 to infinity e to the power minus 2by. For dx we write half y to the power minus of dy, which has to be equal to 1. So, or in other words, these two to cancel out, we get mod a square into 0 to infinity y to the power minus of e to the power minus 2by dy. Now, tell me, do you know how to compute this integral? Anybody knows? Anybody knows how to compute this integral? Y to the power minus half e to the power minus 2by dy, integrating from 0 to infinity. Ritu, any idea?
No, sir.
Ashish? How to do this integral? Y to the power minus half e to the power minus 2by dy, we integrate from 0 to infinity.
Integration by parts, sir.
Substitute 2by.
Yeah, you can substitute 2by. But after that,
Sir, we can convert into gamma function maybe.
yeah, it is. You have to use gamma function. That's the whole idea. Now, gamma function, of course, the gamma function says that if you have an integral like this, 0 to infinity y to the power n minus 1 e to the power minus alpha y dy. The value of this integral can be written as gamma n by alpha to the power n. Is that correct? Yeah. Okay. So this is the formula of gamma function. You can prove it. Okay, it's easy to prove. This is of course then something, but you people are not familiar with the gamma function. Not everyone. Not everybody is familiar with gamma function. Who is not familiar? Okay, let's ask it this way. Who is familiar with gamma function? Here. Ashish, only two people. Tanya? Sanchita.
No, sir.
Tanya. Sanjuk? Heard about
No,
gamma
sir.
function? No?
No, sir.
Okay, but this should have been covered in your BSc. You people have the mathematics in your BSc?
Yes, sir.
Sanchita had, okay. Ritu, you had mathematics BSc?
Yes, sir.
So, Sania?
Yes, sir.
Ashish? Okay, I understand. Yeah. Those people who had BSc in their mathematics, they know about gamma function. This. Okay, anyway, actually, we don't have, this is slightly out of the scope of our discussion, okay? But this is very important in physics because we have to deal with it again and again. The whole idea is this, like if you consider this integral 0 to infinity y to the power n minus 1 e to the power minus alpha y dy. Okay. So let me Okay, we'll get back into this. For the time being, let's use this formula, okay? And if I use this formula, then you can see immediately I can write it as a mod a square, and what I have to do is that I have to set n equal to how much here? N should be, in order to get half, okay, so n equal to half and alpha should be 2b. That means we will get gamma half 2b to the power half. And that thing has to be equal to 1. Okay, now how much is gamma half? Gamma half is root pi. Okay, so that means we get mod a square equal to 2b by pi to the power half. So in other words, apart from an overall phase factor, we obtain this a equal to 2b by pi to the power 1. That means our normalized wave function, finally, that we introduced here is actually psi equal to x equal to 2b by pi 1/4 into e to the power minus bx square. This is our trial wave function. With this trial wave function, next what we will do is that we will try to calculate the expectation value of the Hamiltonian. Up to this it is clear. We will come back to the gamma function. Okay, let us finish this calculation first. Is it clear?
Yes, sir.
Okay. 2b by pi to the power 1/4 to the power minus bx square. Okay, so then let's come back. This is our Hamiltonian. And this is our trial wave function. How much we said? Pi by 2b by pi.
2b by pi to the power 1/4.
Power 1/4 times e to the power minus bx square. Okay, now we will calculate the psi h psi. Okay, so there will be an integration minus infinity to plus infinity. First we have to put the psi star. So we'll have psi star, we'll have psi, and when we combine them, they will give rise to an overall piece of 2b by pi to the power half. Right. Other than that, we have an e to the power minus bx square outside. We have this Hamiltonian and we have an e to the power minus bx. That's it. So this is our expectation value of the Hamiltonian. And we have to calculate this. As you can see, it involves a little bit of integrations, etc. It actually involves two terms. So one is coming from a kinetic energy. From kinetic energy, this is the term minus h bar square by 2m e to the power minus bx square d square dx square e to the power minus bx square. That's it. That is the kinetic. Potential energy plus half m omega square integration x square e to the power minus 2bx square. Right? Here we can do a bypass. Let's first consider this one. Okay, so this let's call it T. Minus h bar square by 2m bx square. d2 dx square. It's not really required, but anyway. Dx square. We can do a bypass over here and transport one of the ddx on this one. Since e to the power minus bx square will always vanish while doing bypass, the first function into integration of second will vanish. Okay, so we'll be left with then minus h bar square by 2m minus integration of differentiation of first into integration of second. Integration of second, the second is only d square dx square of this, so its integration will just reduce the number of derivatives by 1. And this is the term that we have to write. It's clear? Is it clear?
Yes, sir.
Okay. Then, so minus plus we combine h bar square by 2m integration ddx of my to the power minus bx square. How much is this? How much is this if I take derivative?
Minus 2bx e to the power minus bx square.
Yes, exactly. So we substitute it over here and then we'll get how much? 2bx whole square e to the power minus 2bx square. So we are left with then a piece of 4 will come, 4h bar square by 2m. B square also we can take out, x square e to the power minus 2bx square dx. Now again, we can observe the fact that this the integrand of this integration is a even function, right? So we'll, as usual, we'll change the limits, and so we'll have it's how much?